Hey everyone, topic 7 here. Our topic 7 is about, you know how last day we made a graph like this, and I said it wasn't important for us to find the location of the local maxima and the local minima. So today we're going to explore one technique that we can use to find the local maxima and minima. It relies heavily on your calculator, but that's all you're expected to do for Math 30. It is in calculus when you learn algebraic methods for finding these local maxima and local minima. So start off with an example here. So there's y equals quarter times x minus 2 times 2x plus 5 times x plus 4 squared. We're going to use a calculator to find the range. And basically, we're going to use our calculator to find the local minimum or the local maximum, and then you'll know the range. I'll show you what I mean. Go to our graphing calculator here, and into y1, we'll type this function. So alpha y equals 1/4, and then open bracket x minus 2, close bracket, open bracket 2x plus 5, close bracket, and then open bracket x plus 4, close bracket, and then we're going to square that. So there's our function. Check to make sure it matches. If it does, we'll go graph, and we get a picture that's like this. And maybe I'll zoom out just a little bit. So the first thing that I want you to do is to make a rough sketch of this graph. It doesn't need to be anything crazy. And you don't need to have a particularly good scale or anything. So if we made an X and Y axis, it would simply look something like that. Good enough. Doesn't need to be perfect. So maybe just label X, label Y, but I do want you to sketch the graph. Okay, so step 1, sketch the graph. Step 1, sketch the graph. So make sure you include that, and it doesn't need to be anything, it doesn't need to be too precise. From the sketch, we can see that there's going to be a global minimum. So there's a minimum value for this function. And then therefore the range will be y is greater than whatever that minimum is. To figure out the minimum, what we do is we make sure that you can see the minimum on in your window. So you might have to adjust the window settings accordingly to see where it is. And you go second function, and under the trace button, it says there's calc. And then we'll scroll down to minimum, and it'll ask you for left bound. So you move the cursor using the arrow buttons until you are definitely to the left of the minimum, and you hit enter. It'll ask you for the right bound, so you move to the right until you're definitely to the right of the minimum. And then I think on your calculator, there's a third one function that says something about guess. It just tells the algorithm where to start. And you hit enter one more time, and then a display similar to this will come up. So from this, we can see the minimum value is negative 95.47, blah 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 blah. So on your picture, then we're gonna label in the minimum, and we're gonna put in the coordinates. So 0.6667, and then negative 45.97, close bracket. So therefore, the range will be the set of all values, so that set of all y, so that y is greater than or equal to negative 45.97, and y is taken from the set of real numbers. Or if you're doing interval notation, open bracket negative 45.97 up to infinity, just like that. Example B. So here is a cubic function. Before we even do this, with a cubic function and a negative leading coefficient, we know, because it's odd, we know that it's going to start here and it's going to end here. So it's going to come in, it's going to do some funky stuff, and then it'll go down, and it goes up like that. And so we're expecting that the range should be all real numbers, right? There's no way that it starts in quadrant 2 and ends in quadrant 4 without hitting all the y values in between. But let's erase this and let's check. So go y equals, and we'll take this function, negative 4x to the power of, oh, I hit the wrong button. Whoops. Try again. Negative 4x to the power of 3 minus x plus 5 minus x plus, close. Oh, up. Minus x plus 5. There we go. Hit graph. You get this weird thing that doesn't look good. Let's go zoom, go standard view. And look, it's just like I said, it starts in quadrant 2, ends in quadrant 4. So in this case, it actually looks more like little kind of like that. Here's your x, here's your y. And so therefore, the range is set of y, so that y is a real number, no restrictions or anything, or negative infinity up to positive infinity. And that's basically it, I think. Right? Yeah, I think so. Okay. How can we use local minimum and local maximum to solve problems? Well, here's an example. There's a box, and it's made by taking this. This rectangular piece of metal, and we cut out these corners. So we cut out an x by x corner, and we cut out an x by x corner, and x by x, and x by x. So we cut out those 4 corners, and then what we do is there's a little flap that's created right here, and we fold that up, and a little flap that's created right there. We fold it up, fold it up, fold it up, and then eventually you get this box. So let's analyze the dimensions of this box. This dimension right here on the box matches this side length right there. Those two are the same. And so this dimension should be 20 minus x minus this x right here minus another x, which is this x right here. And so it's 20 minus 2x as the dimension. And we probably wouldn't even need to write all of that. I would just do 20 minus 2x. I just wanted to show you the derivation. And in a similar fashion, the dimension along this side would be 10 minus 2x. Okay, so let's find an expression for the volume of the box. So the volume would be the length times the width times the height. The length here is x. The width is 20 minus 2x, and the height 10 minus 2x. So I think that would do it. Hopefully that makes sense. And then there's some restrictions here. We can't have a negative side length. We can't have a 0 side length. So we know that x has to be greater than 0. And then from this one, x has to be less than 5. And from this one, x has to be less than 10. Otherwise, you get a negative side length. And so at the same time, x has to be less than 5. And so the domain restriction, if you put those two together, is, maybe I'll erase all this again. Oops. Showing the thinking, but erase all this. X has 0 has, oh, wrong thing. Oops. 0 has to be less than x, which has to be less than 5. Okay, so there's the domain. That's important. It'll come into play. Oh, shoot, all of that. I didn't realize part B asked for domain. We can just move all of that. Yeah. Okay, so the thinking, all that thinking leads to this: 0 is less than x, less than 5. And so when we write the domain, we're going to do it very formally. It's a set of x such that 0 is less than, equal, less than x, less than 5. And then x is taken from the set of real numbers. Or we could do it in interval notation, which would be 0, 5, and then open brackets there. Okay, hopefully that makes sense. All right, let's determine the maximum volume to the nearest tenth. Okay, to determine the maximum volume, we're going to go back to our graphing calculator. and we're going to figure out what the graph looks like. Uh, we're going to graph this function x times and then 20 minus 2x times and then 10 minus 2x. I think that's our function. Let's double check. Yeah, that looks good. Go graph. Ooh. So you're gonna have to play with the windows just a little bit. Look for. Hey, that looks so ugly. Okay, I don't like this work. How this works. Let's play with the windows. We know that we want to graph x between 0 and something. Actually, let's go -1 up to say about 10. Okay, and the volume. I don't know, like the one side length is 20, the other side length is 10, and then you have some value for x. So the volume's got to be at least about 200, maybe a little bit more. So let's graph from, say, -5 up to maximum value, at least 200. Let's go up to 500 and see how that goes. And you get this function. Ooh, that -5, maybe I didn't like that so much. Maybe let's go -100. Let's see how that looks. Ah, perfect. Maybe just pull. Like, can I do this? Yeah. Okay, so there's a little graph here. But the area that we're interested in is just that first little hump, that first little hill, because that's the area between 0 and 5. So we're going to make a little graph here. So here's our axes. We got x and we got volume. Okay. And then what we see is when x is 0, of course the volume is 0 because then the box has no height. And then when x is 5, again, we get 0 because on the other dimension we get no depth. And it goes up and down, and then the rest of it doesn't really matter. We're only concerned with this part of the graph because that's where the volume's actually defined in positive. Okay, so if there was a way for us to find the maximum here, then we found the maximum height, maximum volume. So therefore, you just go second calculate the maximum, move the cursor over, and a little bit faster. Oh yeah, move the cursor over so it's to the left of the maximum. Move the cursor over so that it's to the right of the maximum. It'll tell you the maximum. We'll go on to our graph. We'll draw in the maximum. We'll put the labels. So x is 2.11325 and the y is 192.45009. Okay, so there's the coordinates. And so what's the question asking for? Determine the maximum volume to the nearest tenth. So therefore, the maximum volume is 192.5. Are there units in this? Centimeters cubed. I think that would do it. Determine the dimensions of the box. Ooh, okay. This isn't too bad. We know that x is 2.11325. So we can say, okay, L is equal to x. So it'd be 2.11325. Let's round to the nearest tenth. Okay, so 2.1 centimeters. The width was 20 minus 2x. And so we'd go 20 minus 2 times 2.11325. And so you would get, the way I want you to do this is, so pay attention here to the calculator. I want you to go into your calculator, 20 minus 2x. When you calculate that maximum, it actually stores that x value under the variable x. And so when you do this, it actually tells you the value, 15.77. And so we can round that and get 15.8. And the height was 10 minus 2x. And again, it'd be 10 minus 2 times 2.11325. And again, when you go to your calculator, you're not going to type in 2.11325. You're going to go 10 minus 2x. Again, the value is still stored for x. So 5.8 centimeters, 5.8 centimeters. And you might make a little concluding sentence, something like, therefore, the dimensions of the box are 2.1 centimeters by 15.8 centimeters by 5.8 centimeters. There we go. Using um, using polynomial functions to solve maximum and minimum problems. This isn't a huge emphasis in Math 30, but it's a very big emphasis in calculus. And in calculus, we will learn algebraic techniques to perform this skill. Okay, hopefully that makes sense. If you have any questions, please send me a message. See you guys on Monday, I guess.